Good morning, everyone. Today we're going to start looking at the sampling distribution for a mean, and we are off and running. So let's go ahead and take a look at what we got. So how tall are high school seniors in California? Attached are the heights of 50 high school seniors in a small high school in the San Fernando Valley. Guess it's not really attached, it's just we just have this histogram. But we can go ahead and from this, this dot plot. From this dot plot, we can estimate, I would say this average is about 170, wouldn't you? Maybe 169. What makes you feel better? 170? Let's do 170. 170 centimeters. Okay. And we can kind of tell because 170 is where the peak is and is also kind of in the middle here. There's this one really short person here and one taller person over here. But they kind of balance it out, maybe a little bit more over to the 140 side. Next, we're going to take a random sample of 5 students to calculate the mean height of the sample, and we're going to do that for 4 samples. Well, over here I've put all of the heights into a spreadsheet, and I've reorganized them. So the first 5, 177, 158, 170, 170, and 170, we took the average of those 5 numbers and we got 169. We're supposed to do this a total of 4 times, but that's just to generate a lot of samples. So when we go back to the simulation that I have, I've already kind of done that. So let's go back to that simulation. So here in the simulation, you can see that I've already done 100 samples, and I've counted up the frequency of those samples and created a dot plot. Look at that. Look at that dot plot. We can copy and paste that dot plot onto our work here. And let's describe the shape, center, and variability of this dot plot. So it looks like this is approaching a normal distribution, I would say. Definitely single peak. Something weird's happening over here where we got a lot of 164s, but I don't know if that's weird or if that's just going to eventually work itself out. So I would say this is an approximately normal distribution. I would estimate the mean to be at about 169 based on where that peak is. And lastly, we don't really have a good way of figuring out variability here. Of course, we could go back to our data and calculate the standard deviation. In fact, what the heck, let's go ahead and do that. Over here, let's figure out the mean and the standard deviation. Okay, the mean is going to be the equals the average, and that's in G, so GG. Good game, everyone. The average of GG. And wouldn't you know it, that's 169. Imagine that. Okay, the next one is the standard deviation. So standard deviation of list G, and that gives me 3.89. Let's say 3.89. Yeah, 3.89. All right. Thank God we did that with some Google Sheets assistance. So let's compare the 2 dot plots. How are they similar and how are they different? Well, this one, they both have similar measures of center, right? So this one we estimated the center was around 170. This one we estimated the center was around 169. So they have very similar centers, measurements. Okay, but the shapes are different, right? This shape we said was approximately normal. This shape here definitely looks left skewed to me. So shapes are different. And then how about the variability? Well, the variabilities are also different. I would estimate the standard deviation over here for the sampling distribution is much smaller. So the variability for the sample averages is smaller. Okay, so decreased sampling variability with the samples. And that's kind of all we really needed to go with. We can definitely generalize based on what we see. The thought just occurred to me that since I have that spreadsheet open, why don't I go back to the population and let's figure out those means and standard deviations. Okay, so we did those ones, and actually look at that. The population mean actually computed to 169 with a standard deviation of 9.61. So we're about a third less. So actually the same center measurement, and if we take a look over here, we've got the factor is about 0.404. So, a little bit more than the third, a little less, somewhere between a third and a half. So what number would that be between a third and 1/2? That's related to, probably would be related to the sample size, right? So we can see what that's going to be by taking a look at our important ideas. So the sampling distribution of X bar, if we take a bunch of samples of X bar, if we took every sample of X bar of size n, we would find that the mean of the sampling distribution, that's mu X bar, is the same as the mean of the population. We saw that directly with the one we just did. Now the standard deviation is the standard deviation of the population divided by the square root of the sample size. And the square root of the sample size would be, well, in our example over here, our sample size was 5. And if we divide by square root of 5, wouldn't you know that's 0.44? Look how close that was, 0.40 and 0.44. I can only explain that we don't actually have this sampling distribution. We just have a piece of the sampling distribution. So that's why we're not exactly divided by square root of 5. But we're close. If the population that you're sampling is approximately normal, then the sampling distribution for X bar will also be approximately normal. So if we took all of the samples of size n, let's say it's 5 in this case, and we figured out what all of those samples could be, and we found the standard deviation, or we looked at the shape, let's go backwards. If we took all of the samples of size 5 that we could possibly think of, and we plotted them, their averages, on a dot plot, we would produce a dot plot that's approximately normal if the population was approximately normal. Standard deviation would be the standard deviation of the population divided by the square root of the sample size. And of course, the center of that sampling distribution would be the average of the population. So now that we have a mean, a standard deviation, and an approximately normal shape, that means we can use the z-score once again. So this z-score, like I was saying last semester, is incredibly important to statistics because now we can use the z-score as a tool even for sampling distributions. So let's go to check your understanding and see how this stuff gets done. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal with a mean that is 266 days and a standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for 270 days. Now that is just the same thing that we did in, way back in, I think, chapter 4 with normal distributions. This is a single pregnant woman, so we'll use the normal tools. Quote normal. Here's a normal curve for pregnant women pregnancies. Now we just need to go until we have kind of sandwiched 270. And 270 is between 266 and 282. 266, of course, was the mean. So we'll put 270 right about here. We'll mark that with a 270. And we need to shade, let's see, more than 270. So more than 270 would be all of this over here. Next, we go to our you know what we need to do over here? Is we need to also say that this is a normal distribution with a mean of 266 and a standard deviation of 16. Now we'll go ahead and get our two equations. First equation, the z-score is x bar minus mu over sigma, and not x bar, just x. That's 270 minus 266 over 16, or 0.25. Next, we're going to say the probability that a z is greater than 0.25, and we'll do that on our normal calculator. And that's 0.4013. So the probability that a randomly chosen pregnancy is greater than 270 days is 40.13. Now let's suppose we took an SRS of 6 pregnant women. So that immediately tells me n equals 6. Let x bar be the mean pregnancy length for the sample. What is the mean of the sampling distribution for x bar? So it's saying what is the mean for x bar? And that's equal to the mean of the population, which we already said was 266. Calculate and interpret the standard deviation. Verify that the 10% condition is met. Well, first of all, let's check the 10% condition. So 10% means that the sample size must be less than 10% of the population. Well, 10 times n is equal to 60 because n is 60. And there's definitely more than 60 pregnant women. So 6 is less than 10% of all pregnant women. Okay, next we're going to calculate and interpret the standard deviation. So the standard deviation for x bar is equal to the standard deviation of the population divided by the square root of the sample size. The standard deviation of the population was 16, so 16 over root 6. That's 6.53. A typical sample of 6 pregnant women has a mean that varies by 6.53 days from the average of 266 days. Next, find the probability that the mean pregnancy length for a woman in the sample exceeds 270 days. This is almost the exact same thing we did before. It's just that now we're going to deal with the sampling distribution instead of the population distribution because we're looking at a sample. When you're looking at an individual, you look at the population distribution. If you're looking at a sample, you look at the sampling distribution. Here's our normal curve again. We're going to mark this with a normal distribution with a mean of 266 and a standard deviation of 6.53. And then we're going to keep marking down until we get to 270. So 266 is right here, 266. That's the mean. And if we add 6.2 or 6.53, we get 272.53 at the 1 standard deviation mark, which means that our 270 should be somewhere between a z-score of 0 and a z-score of 1. mark an approximate location for 270, and we're looking at exceeding 270, so we're going to shade above 270. Now, if I remember this right, the area to the right of a z-score of 1 was 16%. So we're looking at something that's somewhere greater than 16%, maybe somewhere between 60 and 16 and 50% for sure. Okay, we need our two equations. Start with the z-score equation. So notice how this changes now. We now have x bar minus mu of x bar over sigma of x bar. Notice how all of those x bars kind of match here. Okay. So we're going to substitute the numbers we know. That's 270 minus 266 over 6.53. That gives me a z-score of 0.613. Then we write our probability statement. And from our probability statement, we go to our calculator, and we get... Actually, let's go ahead and do this on the calculator. And we're going to go to second distribution, normal CDF, 0.613 to as big a number as my calculator has, which is 1EE99. We're talking about a z-score, so 0 and 1 for the mean and standard deviation. Paste it, and we get 2699. So there is a 27% probability that a sample of 6 women has an average pregnancy greater than 270 days. Notice that down here we're talking about an average pregnancy, and up here we're talking about a single person's pregnancy. And that is all the difference here. The only thing that changes in the calculation, of course, is that standard deviation. And because the standard deviation decreases, the probability is also going to decrease. So we decrease from 40% to 27%. So that's quite a bit, actually. Great, and that's all we have today. We'll see you next time when we continue our look at the sampling distribution for means.